Where is our sun in the Milky Way and how does it change over time? How can you find other people who are as interested in its astronomy as you are? And what if an astronaut throws something off of the International Space Station? Could it hit the Earth? All this and more in this week's Question Show. Welcome to the Question Show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I will gather them up and I will answer them here. All right, let's get on with the questions. Ricky Duroke 9821. Hey Fraser, what is the position of the sun in the Milky Way and how does this change over millions of years? Are we always on the outer rings or do we also move inward? So the sun, the solar system, is orbiting around the center of the Milky Way, just like the rest of the stars in the Milky Way. And when you sort of think about our position, we're about halfway from the center of the Milky Way out to the outer reaches. Where the Milky Way ends is a bit of a sort of fuzzy definition, but let's say the Milky Way is about 90,000 light years across. So half of that's about 45,000 light years to go from the center of the Milky Way to the outside of the Milky Way. And the solar system is located about 27,000 light years from the center. And so if you think about it, there's about 27,000 light years to the center, and then about another 20,000 light years to get to the outskirts of the Milky Way. So really kind of halfway between the center and the outer edge. And the sun, the solar system, takes 212 million years to complete one revolution to return back to its starting point. And so when you think about the fact that the sun has only been around for 4.5 billion years, that's not a lot of times of spins around the Milky Way that we've gone on. It's a very slow process. In addition, the sun bobs up and down throughout its process of going around the Milky Way about 2 times. So it has sort of 2 bobs a little above the galactic plane and 2 bobs below the galactic plane as it sort of completes its orbit. And also, the solar system's path around the Milky Way is slightly eccentric. So when you think about the orbit of the Earth going around the sun, at our closest point, it's like 145 million kilometers. And then at the farthest point, it's like 155 million kilometers. So there's like a slight difference. That's because the Earth doesn't orbit completely. It's a perfect circle around the sun. And the sun doesn't take a perfect circle around the center of the galaxy. It's between kind of 2 to 8% eccentric. And so there's going to be times when the sun is a little bit closer to the center of the Milky Way and times when the sun is a little bit farther away. But also, the sun doesn't follow like a perfect Keplerian pathway around the Milky Way. There's so many other stars. There's so much other objects that are affecting the sun gravitationally that it follows like a slightly weaving, wobbling path because it's sort of being pulled in various directions past star clusters, globular clusters, black holes, and so on as it's completing this journey around the Milky Way. And then the last thing that's kind of interesting is that the solar system is not aligned with the Milky Way. And so if you sort of think about the angle of the plane of the ecliptic, this sort of invisible line that comes out from the equator of the sun, it is off kilter by about 60 degrees from the Milky Way. And so if you sort of imagine the Milky Way as this plane like this, the solar system is sort of like this going around in the Milky Way. So I hope that gives you a better sense of like where we are in the Milky Way. I'm sure you noticed the Stargate planet name that appeared above my shoulder on the first question. That's what it was. It was a planet from Stargate. In fact, and you're going to see more Stargate planet names throughout this entire episode. And this is a way for you to vote, for you to tell us what you thought was the best question answer combo of the week. And so the winner last week was Tim McGuire 9417, 100% solar. Why? This is grossly unreliable. Why not RTG? So this is sort of a question about why Europa Clipper is using solar panels and not an RTG. And I gave an answer, and I guess people liked the question, liked the answer. Very illuminating. Pardon the pun. So I'm going to So we're going to flash a different Stargate planet name up as we go through this episode, and you'll see them collected down in the show notes down below. And just, if you're going to post a comment, just include the planet name, and then we will count up all the votes and we will celebrate here. Joe Raznick. Help, I'm the only person in my family who remotely cares about astrophysics, astronomy, or generally looking up. Friends, same deal. I'm curious what your recommendation is for finding community and conversation in local vacuums. Oh, that's a really tough issue. And then it's not just an issue for space, it's an issue for everything, right? Like you're really into sailing and yet you don't have a boat and there's nobody to sail with. You're really into hiking, but nobody that you really know wants to go hiking. And so you have to go on these solo trips and you're too scared, so you just don't go, right? Like all of these sort of hobbies and interests that you know would enrich your life, and yet you don't have this sort of built-in community. What they want to do is hang out at the pub and they want to drink beer. They want to go and watch the local sports game, and that's not your thing. Or maybe it is, but you also want to do astronomy. And so unfortunately, you need to find that community. And I think, there are plenty of online communities that you can find your way into. You found one here, right? I'm as into space as you are, and everybody on the channel is as well. But we're not people that you can hang out with and go and take a telescope outside and chat and organize star parties. And like there's a pleasure in sort of building these kinds of events so they happen in the real world. So, there's a couple of things that I recommend. One is that there is going to be an astronomical club near to you. I mean, I don't know what town you live in, what city you live in, but in general, any town beyond, a few tens of thousands of people, maybe hundreds of thousands of people, is going to have an astronomy group. And they're going to have weekly meetings, but they're also going to do star parties, and they're going to be out there all the time. And they're great people to go and hang out with and visit. And what's really great about an astronomical club is that you can try out different telescopes. They're going to do their nights where they're out observing, and you can come by and you can check out different telescopes and learn the tips and techniques and see what they like, what they don't like. And so if you're looking to buy a telescope, this is a way that you can do this as well. And if that doesn't work, like if, your closest astronomy club is 200 kilometers away and you're not going to make the commute, then I recommend sidewalk astronomy. And this is where you get a telescope, like a nice Dobsonian or something with a really good view, and you go to some place that is public, like outside a movie theater, or outside a concert, or, some major thoroughfare where people are walking around, and you set up the telescope and you just invite people to look through the telescope. And you get to be there in that moment where people are experiencing space, like the actual physical experience of looking at Saturn or the moon or the moons of Jupiter, in real time. Like you get to be there for this, and that will overfill your astronomy community bucket. And then who knows, right? You may have some great conversations with people, and you'll find other people, and it turns out they're astronomers too, and they really like what you're doing. And then you can go and hang out and do some sky watching, and you just sort of build this larger sense of community. But I think in general, or in the past, before the technology, before the robots came, we had crappy entertainment, and we didn't have really easy ways to communicate with each other wirelessly. And so we had to meet. If you wanted community experience, you had to go and meet people and hang out with them. And now you don't have to. You can watch some guy blather on about space and astronomy on the YouTubes, as opposed to going down to the pub and chatting with your friends. And yet this is a thing that we miss. This is a thing that I think is lacking in our lives. And now, before, it just happened by accident. There was nothing to do, so everybody sat around and told stories at night in the Middle Ages. Well, now we have to artificially sort of take action to make those kinds of communities. And in many cases, everyone out there is in, there's going to be hundreds of people in your town that are craving this kind of space connection. And so organize a science in the pub where you can bring by astronomers to talk in the pub, set up lectures and conferences and sidewalk astronomy. And you got to kind of take action. You got to be the change that you want to be in the world. Good luck. Harun Khan, ZG2VD. I've always had this question in my mind. If an astronaut is doing an EVA and decides to throw something like a tool or anything directly towards the Earth, will it fall? Since there's no resistance, will it travel straight back to the Earth? So this is where orbital mechanics comes in, and you need to start wrapping your mind around how orbits work. So when you are, say, on the International Space Station, you are flying around the Earth at 28,000 kilometers per hour, and you're orbiting at an altitude of about 500 kilometers above the surface of the Earth. And so if you are standing there and you throw, let's say, a wrench in front of the space station and you throw it away from you, and you can throw it at, say, I don't know, 40 kilometers per hour, 50 kilometers per hour, right? Then it is going to start drifting away relative to the space station bit by bit by bit. It's going to sort of move away. Or if you throw it behind you, then it is going to be a little slower than the space station. So that's like the first thing to think in mind. But it's not going to reach the Earth. It's now going to be going at either 28,050 kilometers per hour. It's going to be going at 27,950 kilometers per hour. Still very fast, still in orbit. But the way orbital mechanics works is that if you change the speed of the orbit, you change the altitude of the orbit. You change essentially the shape of the orbit. And so sort of every object that is going around the Earth has what's called the apoapsis and the periapsis. In other words, the highest point in the orbit and the lowest point in the orbit. And so if you're in a perfectly circular orbit, then they're the same. But at the point when you throw the wrench, you are now changing what is a circular orbit into an elliptical orbit. And so now the wrench is going to fly at a certain height away from the Earth. And I haven't done the math. And then it's going to fly around the Earth. And then at the exact opposite point of where you threw it, it's now going to be at a different altitude. And you're going to sort of have changed the orbit of the wrench. But it's definitely not going to get anywhere near the Earth. The only way for you to be able to take your wrench and drop it back down to the Earth is you have to cancel out the 28,000 kilometers per hour, that you have to actually turn that to zero. And then as you throw the wrench at 28,000 kilometers per hour, then it will halt in space and fall directly down. Now, the best way to kind of wrap your brain around this kind of thing is to play Kerbal Space Program. Like I've always said, I learned more about orbital mechanics and rocketry and spaceflight and gravitational assist and all of the Delta V by playing Kerbal Space Program. So if this stuff is kind of interesting to you, I highly recommend playing Kerbal Space Program. Serenity. Our galaxy is in a void. How big is it? It all depends on your definition of a void. So the Milky Way is a large spiral galaxy, and it is surrounded by a collection of smaller satellite galaxies. There's a few dozen. The largest example of this is, say, the Large Magellanic Cloud. There's the Small Magellanic Cloud. There's other even smaller galaxies. And then in our local group, in other words, our sort of local clustering of galaxies, we've got Andromeda, which is a galaxy that's actually a lot larger than us, that is speeding towards us, or maybe we're speeding towards it. And then there's another galaxy called M33 in Triangulum. And so these sort of big three spiral galaxies, the Milky Way, Andromeda, and M33, as well as this collection of smaller galaxies, they form the local group. And when you think about distances, say there's, 2.5 million light years to get to Andromeda. And in cosmological terms, that is close. But then outside of the local group, then the distances start to grow. You're looking at tens of millions of light years to get to other galaxies. When you think about galaxies like the Whirlpool Galaxy or M87, these are tens of millions of light years away from us. And when you sort of add up all of those galaxies, there's sort of hundreds of these galaxies, and they form this thing called the Virgo supercluster. And then the Virgo supercluster, we know, is now kind of moving together as sort of has mutual motion that is sort of, it's not going to come together as a single large blob, but they are sort of affecting and moving together as a group. They're part of an even larger group called the Laniakea supercluster. And now you're getting to structures that are hundreds of millions of light years across, are sort of the largest structures that are out there in the universe. And we're getting these large structures because mutual gravity between all of these galaxies are pulling themselves together and forming these larger sort of concentrations. They call them walls or webs. And you can sort of imagine sort of the as you get this concentration of these galaxies. But then what's happening at the same time, as you're getting the concentration, is then these gaps are opening up in where there are no galaxies. And these are called the voids. And the voids are hundreds of millions of light years across, and they're some of the least dense places in the universe. But when you sort of think about how busy and populated our corner of the universe is, I mean, we live in a city compared to the absolute sort of barren emptiness of the cosmic void. So no, we don't live in a void. We live in a relatively dense part of the universe with lots of galaxies and dwarf galaxies around us, and then even more which are sort of relatively close to us. JC Explorations, is it theoretically possible to travel through a massive black hole and end up in another universe? So we don't know exactly what happens when we fall into a black hole, but when we think about what a black hole is, right? A black hole is a dead star. So you take a star that is many times more massive than the sun, and it sort of has the collapse of its inner layers after it runs out of fuel. It collapses down, you get a supernova, this infalling material compresses it down, and you end up with an object where it is so dense that now the escape velocity from this object has exceeded the speed of light. And so if you sort of consider other objects that are pretty close, like you take a neutron star, right? A neutron star is an extremely dense object caused by a supernova, caused by this implosion. You end up with an object where the escape velocity is just shy, just a little less than the speed of light. In other words, if you tried to take off from a neutron star with the most powerful rocket ever invented, it wouldn't work. If you tried to fire beams of particles at hundreds of thousands of kilometers per second, it wouldn't work. It's only light, only photons finally are going fast enough they can escape the gravitational pull of a neutron star. A black hole is a neutron star, but worse. It's more dense, more gravity than the neutron star. And you can orbit around a black hole. You can go to orbit around a black hole just the way you can orbit around a neutron star, just the way you can orbit around a star, the sun. And so again, we don't know what's inside the event horizon because all of the light that would try to escape that is getting pulled down back into the black hole, that is the event horizon. That is the point where light can no longer escape. And so you can't see it because the light can't get out of it. That doesn't sound like a tunnel to another dimension. That sounds like just a bigger version, a more powerful version of a neutron star. And so if you try to fly your way into a black hole, what would happen is exactly what happened. You try to fly your way into a neutron star. You would sort of crash onto the surface of the neutron star and be smushed down and form this atom thick layer on the outside of the neutron star. And with a black hole, it would be worse. I mean, we don't know what it is, but it's probably worse. And so, the analogy that I was used to think about was, a frog looking into a blender and kind of like, I wonder where that goes. Will it take me to another universe? If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Jim and Jolie Bennett, Rachel Zykla, Paul W., Zombie Eat My Brain, Necron, Grant Verbeck, Cohen, Aaron Gragnot, Craig Chamberlain, Eric Gautier, Voltaire Lechat, Richard Eustick. Join the club at patreon.com/universetoday. Dale Stolte. Can you explain how Mercury is on average closer to Earth than Venus? Yeah. So there's like a meme or it went around for a while. It was an actual research paper that this is based on, that someone calculated how long Earth spends closer to all of the planets. And so if you sort of at every day, you calculate the distance from Earth to Venus, Earth to Mercury, Earth to Mars, Earth to every other one of the planets, then the number of days that Earth spends closest to Mercury is greater than the number of days it spends closer to Venus. And that's just because, when Mercury is on the far side of the sun, it's still much closer than when Venus is on the far side of the sun. So there's only a third of the time when you sort of imagine the orbits where Venus actually sort of comes onto the same side of the sun and it is closer than Mercury. And for the rest of the time, Mercury is the one that's actually closest. And in fact, Mercury is the closest planet on average to every planet in the solar system. And so on average, Mercury is the closest planet to Neptune. And on average, Mercury is the closest planet to Mars. And it's just because Mercury is the closest to the sun and the sun is what everything is orbiting around. And so planets just spend the most time close to Mercury. Christian Desailliers, do different arms of the Milky Way come from different galaxy mergers? The spiral arms of the Milky Way and of all galaxies are kind of weird because they're not what you think. When you look at, say, a galaxy and sort of imagine it face on and you watch as the galaxy is turning and you sort of see these spiral arms, you imagine that the spiral arms are turning, like as the galaxy is turning. And that's not what's happening. The spiral arms are actually a density wave that is moving, is propagating through the galaxy. And so the speed of the spiral arms is different than the speed of the orbit. We talked about at the beginning of this episode that, you know, stars are orbiting around the center of the Milky Way. Well, those spiral arms are going at a different speed and they're not actually a thing. They are a density wave. They are this place where material is being bunched up and then it's being spread apart and then bunched up and spread apart as this, like a, when you sort of imagine a stadium and they're doing the wave, right? As the wave is moving, there's no, you know, individual people aren't moving along to create the wave. The wave is sort of has different people in the wave every second that goes by. And it's the same thing with the spiral arms in the Milky Way. And then as the spiral arms move, they, you know, as they pass a certain region, as they compress that region together, then this often will set up star formation because you've got these diffuse gas clouds, and now the gravity wave is coming by and it's bringing everything together and it is causing the material to be closer, and then that has more likelihood of star formation. And so you look at these really interesting surveys that have been done with James Webb, like the JADE survey, where you've got all of these galaxies, but they're seen in infrared and they're seen face on, and you can see all the pockets of star formation that are that align with the spiral arms. And then as the spiral arm moves past, then this region that was sort of dense and triggered the star formation, then the stars sort of go through their phases. The big ones detonate as supernovae. Then they start to kind of drift apart and break up, and then just join the general sort of star population of the Milky Way. And yet now a new region is having its gas clouds compressed together and turned into new star formation. Anthony Pride. How would we see the farthest galaxies disappear from our sight from Earth? Would one day astronomers just look to see a galaxy is gone, or would they see it pixel away? What do you think? Right, so the universe is expanding, and in fact, the expansion of the universe is accelerating thanks to dark energy. And in about 1 trillion years from now, any galaxy that is not locally connected to the Milky Way. So, you know, I mentioned the local group at the beginning, Andromeda, M33, and a bunch of dwarf galaxies. Every other galaxy is going to be accelerating away from us and will eventually fall over the cosmic horizon. And what we already see is we measure the redshift of the galaxies that are moving away from us. In other words, the wavelength of light that's coming from these galaxies is shifting more into the red. And so what maybe was a very blue galaxy will start to turn into a very red galaxy, and then it will turn into a very infrared galaxy, and then it will turn into a very microwave galaxy, and then it will turn into a very radio galaxy. And eventually the radio waves will be so long that they'll not be easy to measure and detect. And so you won't see the galaxy disappear sort of pixel by pixel as it falls over the cosmic horizon. You will just see this sort of, at the very limits of our observations, we will see galaxies redshifted out to the longest radio waves that we can possibly detect. And so it's understandable that a new civilization that appears in the universe far, far into the future will, and I think maybe the number is 100 billion years, not 1 trillion years. But anyway, some civilization in the far, far future will look out into the universe, and they'll only see the galaxies that are part of their version of the local group, and they won't see any other galaxies, and they won't see the cosmic microwave background radiation. And so all history of the cosmos will have disappeared, and that from their perspective, it will appear that they live in this eternal universe that has always been around, that it never had a start time. But that's not exactly accurate, that there will always be the slightest hints that there is a finite age to the universe, that there will be these galaxies redshifted to the very limits of the radio spectrum, that you could just build larger and larger radio telescopes and tease out that information. And so it's just that they will have to have more advanced technology to get to the place where they will understand the finite nature of the age of the universe. The cosmic microwave background is the first thing that's going to go. Right? Already it is shifted into the microwave, and next comes the radio, and then longer wavelengths of radio. And then eventually the cosmic microwave background will no longer be detectable using the powerful instruments that an advanced civilization is likely to develop early on. Charlie Sink, thanks for the live stream, Fraser. What paths do you think that will lead to human spaceflight becoming profitable? Apart from being able to launch stuff into low Earth orbit, communication satellites, weather satellites, the various kinds of, science satellites, the kinds of stuff that's going on right now. There will be some commercial missions to go to the moon. There will be a lot of scientific missions to go to the moon and beyond into deep space. But we're not going to see the kind of commercialization of spaceflight beyond Earth orbit in the way that we saw in the commercialization of transportation in the past. You think about the age of steamships or even sailing ships as they were moving around the world to find trading partners. It was driving a lot of the investment and a lot of the discoveries that were being made. There's none of that when you go to space. There's no goods to harvest, no resources to gather that you can bring back to Earth that make the mission profitable. It's always, for the foreseeable future, it will be less expensive. So I think in low Earth orbit, things like Starship, there's a lot of new rockets that are coming online to build these enormous constellations of, tens of thousands of satellites like Starlink. But there's not a gigantic demand to go beyond that. And when you think about the way that humanity explored the Earth, a lot of the times there was money to be made. There was new trade routes to establish, new people to trade with. And really, there's none of that out in space. I wish there was a civilization living on Mars and they were developing a different kind of technology and we could trade with them, and that would be really cool. But I think we are decades, if not hundreds of years away from anybody coming up with any kind of commercial reason to go to space beyond low Earth orbit. Kirk Wagner, what do you think will be the first human-made object to reach another star? Breakthrough starshot, solar sails, or a vehicle using future fusion power technology? I mean, we don't know what is going to be the technology that's going to deliver even just a robotic spacecraft to another star system. But according to what we know about the laws of physics, it is a short list of technologies that would actually get the job done. When you think about chemical propulsion, ion engines, even fission rockets, even fusion rockets, that the amount of fuel that you would need to store on board your spacecraft to give you the kind of delta V that would get you to another star system in a reasonable amount of time. I mean, the Voyagers are going to go the equivalent of another star system. It's just going to take them 50,000 years. So if you want to get there faster, you can't use any of those technologies. You've got to use either antimatter. Antimatter is the only fuel that is potentially dense enough to provide the kind of delta V that you need to be able to accelerate to relativistic speeds and then decelerate again at relativistic speeds. And we can only produce maybe a gram of antimatter has ever been produced total across all of humanity. It costs trillions of dollars per gram to produce antimatter. So that's a gigantic challenge. And we can imagine us eventually getting so enthusiastic about going to another star system that we are setting aside 10% of the planet's gross domestic product, or we built some huge orbital factory that's manufacturing antimatter using solar energy, and we have a way to contain it. We put it into a spacecraft, and the probe can go off to Alpha Centauri. And then that's one option. The other option is that you keep the propellant off your spacecraft. And so instead you use like a laser, or you fire kinetic projectiles at your spacecraft to accelerate it to those relativistic speeds. And that's what Breakthrough Starshot is looking at. And there's a really interesting interview that I did about a month back where you probably want a combination of the things, where you maybe use some like a mag sail or a solar sail when you're close by, and then you use pellets of like nuclear pellets that you're firing, like little bombs, to continue its acceleration. There's a whole bunch of different ideas. And just like we have multi-stage rockets that take off from the Earth, maybe you're gonna have a multi-stage interstellar probe. Science fiction has filled our minds with unreasonable expectations about just how complicated, expensive, and technologically infeasible it's going to be to try to travel to another star system in a reasonable amount of time. That the very best ideas that we can think of are 40 years, 80 years, and that it's probably going to be hundreds of years before we really have developed the technology to the point that we can make those kinds of jumps out to other stars. If we want to go fast. And if we want to go slow, then you always run into the problem of the weight calculation, which is like, okay, let's say we want to send a spacecraft, and the best technology that we can come up with will get us to Alpha Centauri in 200 years. Okay. 10 years later, the best technology says we can get a probe to Alpha Centauri in 150 years. In other words, if we had just waited, then the technology would get us to the point that it would be able to do the journey faster. And I would sort of imagine, this enormous arc that's going to make this, this multi-generation ship that's going to make their journey from Earth to habitable planets at Alpha Centauri. And they know it's going to take 500 years with multiple generations, and 250 years into the trip, after 10 generations have been born, the faster ship from Earth comes by, stops, and goes, "Hey, do you guys need a ride?" Right? Like, what was the point of sending the slower spacecraft if you just needed to wait for the faster spacecraft to be developed? And if you take that to its extreme, like if you literally sit down and do the math and calculate when the weight calculation finally makes sense, that there's no chance that you're going to overtake your previous spacecraft, you have to wait like 600 years. So, I almost feel like I can guarantee that if our economy continues to increase, as our energy levels continue to increase, as our technology continues to increase, it will eventually be inevitable that we will be sending an endless stream of spacecraft to other stars at the perfect optimal time when there's just no way to overtake it with a future mission. DanMan64, Fraser, do you own any large telescopes? What are your favorite telescopes? So I don't own a large telescope right now. The telescope that I have behind me that sits on my shelf is like a 90 millimeter refractor. It's a really nice telescope. But I sort of have a tripod, and I go and put it on the tripod if the moon looks nice, or Saturn is up, or Jupiter is up. But most of the time it just sits there on my shelf. And partly it's because I live in the wet coast of Canada, where for about 6 months it just rains and it rains and it rains. And then we get nice skies for about 6 months of the year during the summer. So for me, the right solution is to use a remote telescope. If you remember back in the Star Party days, I was operating this really cool remote telescope out of California, and it looks like that's probably going to happen again. So, I'll keep you posted on what's happening, but sort of some friends are setting up a remote telescope that I'm going to be able to access and share with you guys. And hopefully it's going to be even better setup than it was before. So that's the plan. And, I'm being cagey just because I'm waiting for the whole thing to come together, and I don't have any details yet. But in theory, I will have access to and be able to live stream a very powerful telescope in the coming months. And then the telescope that I'm planning on getting, I'm planning on getting a Dobsonian telescope for just having here on the property. And that's the one that I recommend everybody, is the Dobsonian. It's a general term. They call it a light bucket. They're very easy to use, very powerful, very inexpensive compared to other telescopes of the same size, very quick to point and direct. They're ideal for like sidewalk astronomy, where you're trying to show people Saturn, the moon, and so on. They're very easy to kind of point at different objects. So that's the one that I recommend. An 8-inch Dobsonian telescope, 10-inch if you can afford it, but I would go with either a 6-inch or an 8-inch. Jonathan Gariepi, could supermassive black holes be made of the lost antimatter that was created during the Big Bang? Yeah, so the lost antimatter, the lack of a balance between the amount of matter and antimatter in the universe is a puzzle. And this is one of the big questions that astronomers have, that in theory, there should have been equal amounts of matter and antimatter in the universe after the Big Bang. And we know that there were almost the same amount, but they weren't quite. And so in the end, we live in a matter-dominated universe and not an antimatter-dominated universe, or one that is equally balanced. And so, people always ask various versions and flavors of this question, like, is the antimatter out there somewhere? And so the answer is no, because when matter and antimatter meet with each other, you get this enormous blast of gamma radiation, like the sort of pure E equals MC squared formula version of energy. And so if there was clouds of antimatter out there floating through space and they interacted with clouds of matter, we would be seeing just this gamma ray glow in all directions, or wherever these collisions are happening. And we just don't see that. I mean, we see gamma ray coming from gamma ray bursts, and we see it from the accretion disks around supermassive black holes, but we don't see this generalized gamma radiation that's coming from large clouds of antimatter and matter finally meeting with each other. And you could imagine, like, there are galaxies made of antimatter out there in the universe, but they would be interacting with matter. Like, wherever the line is between the matter and the antimatter, we would just be seeing enormous amounts of gamma radiation. We just don't see it. So, but the question that you're asking, I mean, it's kind of interesting, because inside a black hole, it doesn't really distinguish between whether something is made of matter or antimatter or energy or whatever. That, the classic question, I've answered this many times in the past, is like, if you had a black hole that was made of matter and you had a black hole that was made of antimatter, and you put the two of them together, what would happen? Would they cancel each other out? Would they explode? No, that you would get a black hole with twice the mass. And that's because once you get inside the black hole, there's no real distinction between whether you're matter, you're antimatter, or whether you're light. And sort of think about that, right? Like, if the escape velocity of the black hole is greater than the speed of light, and you took a black hole's worth of antimatter and a black hole's of matter, and you combine them together and they turn into pure energy, well, the pure energy can't escape the, can't escape the event horizon of the black hole. And so you wouldn't see anything. And so in fact, you could take just energy and you could just compress light down into the same kind of enough density that it would form a black hole. And something that's called a Kugelblitz. And so there's just no distinction. And so, it'd be really weird that all that antimatter just ended up inside the black holes and not in spilling out into other regions of the places where those black holes are feeding on to add themselves. And if there's any antimatter mixed in with that, then we see the gamma radiation and we know that was going on. And we just don't see that. We just don't see the evidence of antimatter out there in the universe. Larry Fields, are any parts of the ISS reusable instead of burning them up? See, unfortunately, the International Space Station is going to be deorbited in 2030. So in about 6 years from now, when I'm recording this, they're going to bolt on a sort of modified version of a SpaceX Cargo Dragon with a whole bunch of engines and a bigger fuel tank. It's going to fire all those engines, and it's going to deorbit the International Space Station into the deepest part, or the most remote part of the Pacific Ocean, the chances of it doing any damage to anyone on Earth, to sort of minimize that damage. And it sounds like a waste, right? You've got this thing that humanity has been building for 25 years that's hundreds of billions of dollars have gone into the construction of the International Space Station. It has hosted hundreds of astronauts. I think we're up to Expedition 70, mid 70s anyway. So I'm sure by the time they'll be closing in on the 100, right? Expeditions of astronauts of varying numbers, that they're in some cases we're up to 10 people in space on the station. Like, it's amazing that we've done this. And yet it feels like a cosmic tragedy to bring this vehicle down. And I think a lot of people who are watching this, a lot of people, when they hear this is going to happen, they're like, no, this can't happen. Why? And then there's the bargaining, right? We're just like, okay, well, maybe private companies could take over and manage it. And so there is plans to dock a commercial, like a private commercial space station module to the most usable parts of the station post deorbit. And so the proposal is maybe before the space station is deorbited, they will detach this sort of commercial nexus from the station that consists of this private thing and maybe a couple of other modules. And that will go on to form a new private commercial space station that will remain in orbit. And so bits and pieces of the International Space Station may remain in orbit. But my experience in reporting on this stuff for 25 years is that none of these commercial projects work out. They don't pan out. That people find investors and they have a plan and they, in some cases, build prototypes and hardware and then they go out of business. And so, I mean, we've seen SpaceX, and SpaceX has been able to pull off really an amazing feat in reusable rocketry and bringing down launch costs and bringing on customers and building up this network of Starlinks and so on. So like they're the exception, but the rule is that these things don't happen. They go out of business. They're too expensive. The investors bail, and the thing never comes together. So I think even though there are, various people are talking about commercial space stations, I hear less and less about a lot of those projects, and that makes me think that, okay, maybe people are running out of money. Maybe things are getting a little more difficult. And I think that the default, the thing that you would just have to assume is going to happen is that in 2030, when the funding runs out, the SpaceX Cargo Dragon will dock to the station and it will deorbit the station as planned. And then the international community will no longer have their space station. And that sucks. But there's a limited amount of money that's being given to this by the various governments. There are new priorities with the moon, and this is just how it works. All right, those are all the questions that we had this week. So thank you everyone who took a second and put a question into the YouTube comments so that I can gather a bunch of them here and answer them. But also everybody who joined me for the live chat here on YouTube. We do the show every Monday at 5 p.m. Pacific time. It's 2 hours long. When you think about the length of this one, 2 hours. And then we have the part that we edit down for the Q&A, but then another hour that we call overtime. So if you want to come and hang out, it's a really good time. Chat with other people about space right here on the YouTube channel. Now, I'm going to talk about another show that I do, but first I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Barry Lake Roofing, David Gilton, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, ScienceWorldRecord.org, SpiderSwap.io, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So in addition to the question show coming back from its hiatus, we just have also returned to recording Astronomy Cast. And for those of you who don't know, I do a long-running astronomy-related podcast with my co-host, Dr. Pamela Gay, and we are in the 720s episodes now. We've been doing this show for 16 years. I'm sure it's more. I never remember how many years old the podcast is. We're often in the top charts for astronomy-related podcasts on various podcast lists. And so if you want, while this is kind of, very much sort of talking about a ton of different topics, with Astronomy Cast, it is laser focused. We are picking one topic in astronomy every week, and we are trying to cover it soup to nuts. Supermassive black holes, quasars, various forms of radiation, planets, like 700 episodes, there's a lot of topics. And so you can sort of jump back and forth and pick the topics that you like. My co-host, Dr. Pamela Gay, has the best voice. And so if you want to listen to somebody who really knows space and astronomy, but also has just an incredible speaking voice, I think you'll really enjoy Astronomy Cast. And She has been my professor when you sort of think about the fact that I've been doing this work for 25 years, but much more than half of this, I have been doing Astronomy Cast with Dr. Pamela Gay, and I've asked her all my questions, right? And she has been able to patiently answer them. And if you go back to the beginning of some of the early episodes, you listen to my questions, they sound very similar to the kinds of questions that you're asking me. And that's just because like these questions are universal. And she has patiently over the course of more than 700 episodes really given me my education in astronomy knowledge to this point. So a huge sort of shout out to Dr. Pamela Gay. And also just if you want like more wholesome astronomy content, the kind of thing you can put on with the family, I think you'll really enjoy Astronomy Cast. So check that out. All right. We'll see you next week.